Hello, everybody. My name is Lance Dixon, and I bring you greetings from sunny California. And it's my job to be your tour guide for the next 4 hours or so through the area of the Amplitude games we call Bootstrap. So let me bring up my slides here, and I should share screen. So Bootstrap is or the Amplitude Bootstrap is an interesting area I want to tell you about. And I like this quote from Yukawa, which I discovered earlier. Those who explore an unknown world are travelers without a map. The map is the result of the exploration. The position of their destination is not known to them, and the direct path that leads to it is not yet made. Or a little less elegant way of saying it is, if we knew what we were doing, it wouldn't be called research. So I want to take you on this tour, which is kind of experimental mathematical physics, by first defining for you what bootstrap it isn't, because there are lots of usages of the term bootstrap. One of the things it isn't is the conformal bootstrap. This is a very interesting approach to constraining allowed conformal field theories in various dimensions by using general constraints like crossing symmetry, positivity, and so on. But it also allows you to hone in on particular theories once you make certain other assumptions. Here, for example, you get very precise information about the critical exponents in the Ising model. Another thing it isn't, although it has a similar name, is the S-matrix bootstrap. S-matrices and amplitudes are more or less synonymous, but the S-matrix bootstrap refers to a program which has also come to rather successful fruition in the last couple of years. And it constrains S-matrices for general massive theories, again, using general principles like unitarity and crossing symmetry and so on. Instead, what we're going to talk about in these lectures is the Amplitude Bootstrap. And it's different in that we often pick a very specific theory. And for all the examples I'm going to tell you about, it's planar n=4 Super-Yang-Mills theory. And then we explore the scattering amplitudes in that particular theory in rather great detail. For example, to very high loop order and as a function of quite a few kinematic variables in some cases. And we do this by making specific assumptions about their functional dependence. And those assumptions are often dictated or suggested by lower loop results. And then the strategy is to write an ansatz or a guess as a linear combination of such functions for the amplitude at the next loop order. And then we constrain this ansatz with known or suspected properties of it until it's uniquely determined. But because we didn't calculate it directly, we should check to make sure that the answer is right. And so we should check the answer with known constraints. And if it passes all those tests, then we declare it to be solved. And then after we have solved it, it's often presented to us in a rather nested form. And so there's also some more work to extract numerical values of the amplitude and also its analytic properties. And we do so whenever and wherever we can. So that's the general framework. And some of the specific successes of this Bootstrap program so far have included, for example, the scattering of 6 gluons to 7 loops. So here I show one of the approximately 1 billion Feynman diagrams that would contribute to the scattering of 6 gluons in this theory. And over here, I show the numerical results for the remainder function, which is essentially the logarithm of the amplitude after removing some divergent parts, evaluated on a one-dimensional line through the space of possible kinematics. And what you see here is that the results are amazingly similar in a particular region. Here is the point 111, and all these results have been normalized to go through that point. But when this cross ratio, this variable u, is smaller than 1, the results are all extremely close to proportional. They look a little bit different out here. Notice that these are the individual coefficients of that loop order, not the partial sum. So every single loop coefficient looks almost exactly like every other one, from 2 loops up to 7 loops or so. So this is just one example or a teaser of the kinds of results we can get with this Bootstrap program. I also want to say that besides getting out numerical results, you can also mine the results for patterns. And this is something that we're still in the early days of doing. So there's a huge amount of structure in these high loop order results. And there are many analytic limits to study, and also perhaps many patterns in the coefficients to explore, because these functions depend on multiple variables. In the 3 examples I'll talk about in these lectures, they're functions of 2, 3, and 6 different variables. And most high loop order results tend to be single numbers, such as beta functions or anomalous dimensions. So that's sort of a taste for what we're going to see. And here's a more detailed outline. I've split these into 4 lectures of about an hour each. In the first lecture, I'll go through general properties of amplitudes in n equals 4 super-Yang-Mills, and also its planar version, which we'll study mainly. And I'm also going to introduce to you a new arena for bootstrapping, which we've only been engaged with since last December, a certain form factor, which I'll describe later, but it's actually simpler in many ways, so it's a good way to get started. In lecture 2, I'll describe generalized polylogarithms and symbols and how they fit into this construction. They're really at the heart of it. And we'll also discuss infrared divergences and amplitudes and various types of normalizations that one can use to define the finite parts. Then we'll move on and discuss branch cut properties, which lead to various other relations, and how to construct the space of functions for a given problem using the form factor example. Then in lecture 3, we'll talk about how to find the amplitude in the space of functions with the aid of various constraints. For example, there are constraints on what we call the final entries of the symbol. And there's also the need to impose boundary conditions from somewhere. And in the case of the form factor, it's something called the form factor operator product expansion, which only became available recently. Then I'll show you some results of applying all this procedure to the form factor case. And then finally, in lecture 4, we'll turn to the scattering of just n gluons for n equals 6 and 7. Although this is just one lecture, most of the techniques have already been developed in the first 3 lectures. So I'll spend more time just on various results and other limits that are available in this case. So on to lecture 1. Now, in general, there are various ways to compute amplitudes in perturbation theory. In principle, every amplitude can be computed using the method of Feynman diagrams. So in that method, you enumerate and draw all Feynman graphs. And then you look up the Feynman rules. And if it's a big problem, you teach your computer the Feynman rules. And those Feynman rules, when applied to each graph, give you a partial integrand, which has to be integrated over the virtual momenta at a given order in the loop expansion. Then, after evaluating the Feynman rules for the loop integrand, you need to perform all the loop integrations. And this is often the hardest step. The computer algebra generates can be used to generate the graphs and evaluate these rational functions, but actually doing the loop integrations is a big difficulty. Once you've done all of them for individual graphs, you add them up and you get your amplitude. Of course, as you've been learning in this school, there are many other ways to do things. For example, you could construct the integrand in a different way, which isn't graph by graph. One way to do that would be to evaluate all unitarity cuts and use that information to construct the integrand. Another way to do it, which Jake Bergili has mentioned, is that there is a all loop integrand for some theories like n equals 4 Super-Yang-Mills. Sometimes that integrand does not come out in a local way, which looks like, which has all the causal prescriptions to let you integrate it easily. So sometimes you need to rearrange it into a local form. But if you have a local form, then you can, in principle, perform all the loop integrations. And they're often fairly similar to the ones you would do in the Feynman diagram method. And then after you've done that, and you often break things up into pieces with different loop integrals involved, you would rewrite the answer as a sum of such integrated quantities. Now, in special cases, like the ones we're going to talk about in these lectures, you can do things in a quite different way. Instead of doing every single loop integral, you basically guess what are all the possible loop integrals you could have and write down a function space which includes those functions. And then you write the amplitude as a linear combination of the functions in this space, where these coefficients Cm are unknown rational numbers. And then after you've done that, you have a guess which depends linearly on these variables. You have a bunch of constraints. These constraints amount to linear equations for the variables. And you solve all those equations, and then you find some known rational numbers, plug them back in, and you're done. So you bypass the problem of performing loop integrations, except of course you have to know roughly what space those loop integrals should lie in. Now let me just say a few words about the particle content of n equals 4 Super-Yang-Mills theory. I'm not going to go into great detail about it, but I thought it's useful to mention a few things about it and its relation to QCD. So n equals 4 Super-Yang-Mills theory is a Yang-Mills theory, so it has gluons that interact through a non-abelian vertex. And the matter content includes 4 massless spin-1/2 gluinos and 6 massless spin-0 scalars. And all of these states transform in the adjoint representation of the gauge group. And in these lectures, we're always going to take the gauge group to be SUNC, where NC is the number of colors. And usually we're going to take this number to infinity. So that would be the large N limit. Now, supersymmetry acts on the states in this multiplet. And the on-shell states are characterized by helicities, these massless particles. The gluon has helicity +1, and its CPT conjugate has helicity -1. And if you act with any one of the 4 supersymmetry generators, you generate 4 different gluinos, and supersymmetry changes the helicity by a half unit. So you get the +1/2 helicity gluinos. If you act again, you have 4 more choices, but remembering that the QA's square to 0, you only get non-trivial things when you use the combinations of them, QA, QB, and that ends up being antisymmetric in A and B. So you get 6 different states at the next level, the 6 or 4 choose 2 states that correspond to the labels of the scalars. This index is also called the R index label for the SU4R symmetry that this theory has. If you act 4 more times, then you need to be anti-symmetrized in 3 things, and that 4 choose 3 is 4 states, and those are the -1/2 gluinos. Finally, when you act 1 more time, there's a unique gluon with helicity -1. So for each color, or for each adjoint term in the adjoint representation, you have a total of 16 states. So that's 1 plus 4 plus 6 plus 4 plus 1. And they're all in a single multiplet. And because of that, the symmetry word identities that relate amplitudes with different external states are quite powerful. For example, in one sector we call MHV, there's essentially one super amplitude that encodes the amplitudes of many different component fields. And of course, QCD is not unrelated to n equals 4 super Yang-Mills theory. You heard a lot about QCD in the context of jet physics in Alexander Huss's lectures earlier. And as you know, QCD has gluons, but the matter consists of quarks, which are in the fundamental representation of SUNC, where NC equals 3 in the real world. And so the difference between QCD and n equals 4 is to replace the quarks with 4 copies of fermions in the adjoint representation and add 6 real adjoint scalars. But the Feynman vertices have very similar space-time structure. These self-interactions of gluons, those Feynman vertices are identical. So here's the 3 gluon vertex, it's exactly the same. The interaction of the fermions with the gluons is kinematically the same. There's a gamma matrix in both cases. The only difference is that this gluino has a sort of extra color. If you think of the color adjoint as being an NC cross NC bar, it has an extra NC bar label. And of course, you have to subtract singlets if you're not at very large N. Okay, and then there are the additional scalar contributions, which include, for example, the coupling of scalars to gluons through the gauge vertex for scalars, and there are also Yukawa couplings. But the interesting thing is that the matter, if you have a gluon producing it, it's always produced in pairs. And this has an interesting consequence, which is that tree level, the QCD and n equals 4 amplitudes are essentially identical. So in particular for n gluon amplitudes, if you write down all the tree graphs here for an n gluon amplitude, you see that the fermions and scalars never appear. And that's because of this feature that they don't get produced singly. For fermions, that's pretty obvious because of angular momentum conservation. If you have things that have integer spin, you can't make a single half integer spin state. You can only make pairs. But it's also just explicitly true from the Feynman rules for scalars. As a result of this tree graph and all the other ones that would contribute to this process are exactly the same in QCD and in n equals 4 super Yang-Mills theory. And that means that QCD actually has to obey identities that you could prove using supersymmetry. And I'm not going to go through the proofs of those identities here, but one thing you can prove using just n equals 1 supersymmetry is that the gluon amplitudes with all positive helicities, when these are outgoing, or just one negative helicity, those have to vanish. And so that's not only true for QCD at tree level, but it's also true for n equals 4 super Yang-Mills to all orders in perturbation theory. So for QCD at tree level, and also for n equals 4 super Yang-Mills, for an n gluon amplitude, the first non-vanishing type are what we call the Mhv amplitudes, and those are the ones with 2 negative helicities. So if you have only 1 negative or no negative, you get 0. If you have 2 negative, you get something which at tree level is called the Park-Taylor amplitude. And you may be familiar with that formula by now, that it has an ij to the 4th in the numerator and some cyclic string in the denominator. And in particular, if you divide it by that numerator factor, you get something completely independent of I and j. And so that fact is really a consequence of n equals 4 supersymmetry. And we'll use that fact later when we look at MHV loop amplitudes, because in n equals 4 super Yang-Mills, this identity is still true at any order in perturbation theory. And what it amounts to, if we color order these amplitudes, then again, it doesn't really care where the two negative helicities are, and the color ordered amplitudes will only depend on the dihedral, the color ordering. And that means that they're invariant under certain dihedral transformations that rotate and flip the diagram. Now, this equality between QCD and n equals 4 super Yang-Mills is true at tree level, but at the quantum loop level, the theories start to look quite different. It was recognized quite a while ago that n equals 4 super Yang-Mills remained very special at the loop level. In particular, when we looked at quite a while ago, the cancellation of loop momenta in the numerators of n equals 4 super Yang-Mills amplitudes, we found that there were only scalar box integrals in the representation of the result. And these scalar box integrals, you could just compute them explicitly, and you discovered that we are what we call weight 2 functions now, or just dilogarithms. So for example, if we took a 5 gluon process, there were some terms where 2 of the gluon momenta joined at one vertex, and the other 3 were running into the graph in the form of this box integral. We call this a one mass box because these 2 legs together, even if these lines are massless, become an external mass, whereas these are actually massless arguments to the box integral. When you work out this integral, you find that it has dilogarithms, and the arguments involve the kinematic invariance in a very simple way, where S12 is the Mandelstam variable for these 2 momenta added up, squared, and S123 is also this invariant that comes from summing these 3 by momentum conservation. And of course, also S23 enters. So the boxes were all essentially dilogarithms, or things that also were like squares of logarithms. On the other hand, the QCD results, which could be computed back then, were quite different because they also had single logarithms and rational parts from different types of integrals. For example, triangle integrals like this, sometimes with tensors in the numerator, or bubble integrals. And this bubble integral, it has a 1 over epsilon pole, which is ultraviolet in nature and can be associated with a beta function in the overall amplitude. And then at order epsilon of the 0, it has a single logarithm, in contrast to these double logs and dilogs. So there are also rational parts at order epsilon to the 0 in the QCD results. But n equals 4 had these weight 2 functions appearing. Since then, of course, we've been able to compute things explicitly to higher loops, and it's added to the evidence that n equals 4 super Yang-Mills amplitudes have a certain uniform weight, or transcendentality, which always has the same value, 2L, at loop order L. And this is an example of a fundamental assumption that we make when bootstrapping these amplitudes. We have to define this weight more carefully later, but for a more general class of functions. But basically, the weight is the number of integrations. For example, a logarithm can be defined as integrating a rational function 1 over t dt from 1 to s, or d log t, not surprisingly. Since there's one integration, we say that a logarithm has weight 1, and a dilogarithm, not surprisingly, is the integral of a log, and so that is weight 2. And then the n-fold classical polylogarithm, LIN, is similarly defined by integrating LIN minus 1 or dt over t, and therefore this one extra integration will give it weight n. Now, this is not at all the complete set of functions that we need to define, but it just gives you a glimpse of how we're going to have these this classification of, or grading of, the function space by the weight. And at loop order L will always pick out a function from somewhere in the weight 2L sector of whatever space it is we construct. So this feature of n equals 4, that we always get uniform weight, seems to be valid for any gauge group, although it hasn't really been investigated in a huge amount of detail. But most of the efforts in going to high loop order in n equals 4 have been in the planar limit, or the limit of large NC, where the gauge group SUNC becomes very large. In this limit, a Tuft showed how to do a color analysis using double lines and showed that only planar Feynman diagrams contribute to the amplitude. When all the diagrams are planar, and we mean planar when you hold fixed the legs out at infinity. So we send the external legs out to infinity in some direction, and then all the graphs that you draw fit in a plane. And when that happens, you can see that the only important kinematic invariants that enter the Feynman diagrams, they should all involve only color adjacent combinations of momenta. So they should be subsets of the n momenta that are next to each other, starting say at ki and going around to kj minus 1 mod n. Whenever those are the only important variables, you can rewrite things in terms of dual variables. So with planar graphs, you can always define a set of dual vertices that live in the wedges between these momenta. And then all of these important variables can be rewritten as differences between two dual variables. So the difference between x1 and x2 is k1, x2 minus x3 is k2, and so on. And then any one of these adjacent sets is just a difference of two dual variables, which is x1 minus xj squared. These are 4 vectors. And then we get this scalar invariant quantity. Now, as we'll see in a second, planar n equals 4 Super-Yang-Mills has an even more restrictive property called dual conformal symmetry. And that is generated by translations and boosts and a dual inversion. These xij squareds are automatically invariant under translations of all the x's by the same amount. And because they involve a Lorentz invariant contraction, they're also invariant under Lorentz symmetry. But this one extra symmetry, which we'll get to in a second, is to invert these coordinates. So you take x, the vector xi, and multiply it by 1 over xi squared for all I simultaneously. And when you do that, you find that the xij squareds get replaced by the same xij squared divided by xi squared xj squared. I'll leave that as a little exercise to verify that this transformation leads to this relation for the xij squareds. Now, where does this symmetry come from? There's one way of seeing it, which goes to the ADS Cft duality. The theory n equals 4 Super-Yang-Mills is a theory that lives in 4 dimensions, a conformal theory that lives on the boundary of a space which is ADS 5. And strings propagate on this space. There's also a hidden S5 sphere, not shown here, but the symmetries of the sphere are SO6 or SU4, and that's the R symmetry I mentioned earlier of this. So that's one symmetry, but ADS5 has the space-time symmetry, which is SO4, 2. And this is also the symmetry group of a 4D conformal invariance in conformal invariant theory in 4 dimensions. And this extra variable is a scaling transformation. This radial variable corresponds to things happening on different length scales. So this is this holographic interpretation. And Aldai and Maldacena 2007, studied the scattering of gluons from string theory in this ADS5 picture. And they realized that the this dual conformal invariance was a consequence of a symmetry of string theory called T duality. So T duality is a Z2 symmetry that exchanges the string worldsheet variables sigma and tau. So if you have a string and you're looking at it at long distances, if the string tension is very large, it's quite short, and there are small oscillations around the center of mass, but basically there's a center of mass that looks sort of like a particle at long distances. It's moving along it with momentum k mu. When you go to this dual picture where you've exchanged sigma and tau, then this role of tau as the coefficient of the time dependence of x now gets transformed into sigma. And sigma is the worldsheet variable that extends along the string. And so if you have a term k mu sigma, it means that from one end of sigma to the other, the string stretches this long distance k mu. So if you have a large number of strings that are interacting together in an amplitude as external states, and you make this T dual transformation, then the worldsheets will now be separated out at the infinity of the scattering process. Each incoming string will correspond to a light-like vector k mu. So we get this picture here drawn by Amit Sever a little later, which involves a closed n-gon at the boundary of this ADS space. And this closed polygon comes from this picture here. Each of the segments corresponds to an asymptotic gluon with momentum k, but after T duality, it becomes a vector boundary condition. And then you have the holographic direction where you're allowed to move away from the boundary into the bulk of ADS5 in the middle of the scattering process, where momentum transfers are high and you're at short distances. In the strong coupling limit of planar n equals 4, that becomes a semi-classical limit of string theory. So in that limit in which the number of colors is large, but also NC times the coupling squared is large, you can compute these amplitudes by minimizing the area of this worldsheet subject to these boundary conditions. And these boundary conditions depend on the momenta, so they're set by the kinematics. And so you have a minimal area problem, a very strong coupling, but you also have an argument for why the answer should have this symmetry. It should be a conformal invariance after you switch to these T dual variables. And so the answer should really only depend on conformally invariant combinations of the positions of these polygon vertices. So there's two things that go together, which is dual conformal invariance and the notion that these amplitudes are determined by polygons. And in the strong coupling limit, where there are many, many gluons sort of making up this world sheet, you get a picture like this. But at weak coupling, you can also have a polygonal contour, and you can calculate the expectation values of Wilson loops by sending a few gluons around these contours. And these calculations were done soon after Alday and Maldacena's suggestion, and it was found that this was an alternate way to calculate the space-time scattering amplitudes. Instead of having Feynman diagrams with external gluons going off to infinity, in n equals 4 super-Yang mills, you could also calculate these vacuum expectation values of these closed contours. Now, the symmetry group that you get by including this inversion symmetry turns out to be 15-dimensional. That's the conformal group. And well, we're very familiar, of course, with the Lorentz symmetry, which includes rotations and boosts and translations. There's also overall scaling or dilatations, which are not spoiled at the quantum level if the beta function vanishes. But usually along with that, you also get, so now we get the sort of special conformal transformations as well in the conformal group, but we're supposed to act with them not on position space, but on these dual momentum variables, the xi's. So the really non-trivial generators are special conformal transformations. And there are 4 of them, but they correspond to a discrete inversion and then a translation in any of 4 directions, hence the 4, and then another inversion. So rather than checking the conformal transformations themselves, it's sufficient to check or impose invariance under the inversion. And so we need to just impose that our functions, which if we make them functions of xij squared, we get all of these symmetries automatically. And if they're scale invariant ratios, we'll get this. But then we want to build them to be invariant under this transformation too. So we have a Wilson n-gon, which has n positions. We want to impose this requirement on it. And the way to do that is to ask that the answer is not a function of arbitrary xij squareds, but only a function of cross ratios, which we label by ij, k, and l. And we write xij squared, xkl squared in the numerator, and xik squared, xjl squared in the denominator. And when we do that, this is another exercise for you. If you plug in this transformation, relabeled appropriately 4 times, you will see that all of these xi squared, xj squared, xk squared, xl squared cancel between numerator and denominator. So these arguments are invariant under this inversion symmetry. And therefore, if we write everything in terms of these functions, we will find that characterizes the dual conformally invariant answers. Now, another exercise for you is to convince yourself that when we have a light-like polygon, or we have adjacent xi I plus 1 squareds that vanish because they correspond to massless gluon momenta, that there are no such variables that you can write down. There are no independent invariant cross ratios. And on the other hand, once you go to n equals 6, you can find exactly 3 of these, and here they are. So it's convenient to write a hexagon here and to draw the lines for the corresponding invariants in the numerator as solid lines and dashed for the denominator lines. And you always need to have a dashed and a solid coming from the same vertex, because you need to have the same number of 1s, 3s, 4s, and 6s upstairs as downstairs. So this is an example of the cross ratio U, which has these combinations in the numerator and these in the denominator. We can translate this back to the Mandelstam variables by recognizing that x13 squared was the sum of k1 plus k2 squared, which is usually called S12. So that's a 2-particle Mandelstam variable. And similarly, S45 is x46 squared. And that's a 2-particle invariant involving the momenta k4 and k5. And in the denominator, because these guys are separated cyclically by 3, this one becomes S123 and S345. So these are what we call 3-particle kinematic invariants, or Mandelstam variables. So that was just one of the dual conformal cross ratios, but the other 2 are related by a cyclic symmetry, where we let all the labels I go to I plus 1. And that just rotates this box around. And then we read off from it the corresponding momenta, or x's if we want, entering the next conformal cross ratio, which we call V. Finally, there's a third one, W. But if we rotate one more time, you'll see we come back to the original U. So although this hexagon has 6 points to it, the dihedral symmetry or the cyclic rotations acting on U, V, and W comes back to itself after just 3 rotations. Now, if we do the same analysis for the 7-point case, we'll find that there are 6 ratios. Basically, every time you add an extra point to a scattering amplitude, you can characterize the momentum of that massless particle by 3 components, the 3 spatial components, because the energy is not independent. It's just the magnitude of the spatial momenta. So you need to add 3 degrees of freedom every time you add one more external particle. And the dual conformal constraints reduce the number by the same amount for each one. So you get to add 3 each time. And so the general number of ratios will be 3n minus 15 to match this sequence, 3, 6, 9, etc. So if we want to bootstrap 6 gluon amplitudes, we're going to find that we need functions of 3 separate non-trivial variables. If we were to do it in a non-dual conformal theory, we would have 5 more variables, or if it's also scale non-invariant. So bootstrapping a 3-dimensional function is easier than an 8-dimensional function. In the n equals 7 case, there are 6 ratios, which is starting to be a quite high dimensional space, but one can still make progress on this. So here's a sort of overarching big picture of the situation for planar n equals 4 super Yang-Mills. I haven't told you everything about this yet, but this is the planar coupling, lambda, which involves the Yang-Mills coupling squared times the number of colors. That's held fixed in the planar limit. So one parameter you can vary is this coupling, the 't Hooft coupling. You can also vary the kinematical variables. Of course, there are many kinematical variables, and the number depends on the number of external gluons. And this is just some one-dimensional slice through that. Now, out of very strong coupling, as I mentioned earlier, this is dual to this semi-classical minimal surface approach. And there are some very nice techniques for solving the minimal area problem. So we basically understand what's going on up at very strong coupling. In perturbation theory, we can start to build up information which you could think of as discrete lines, order by order in perturbation theory. But over here on the left, in a particular collinear limit, which we'll talk about a little later, there's another approach due to Basso, Sever, and Vieira, after earlier work with Gaiotto, Maldacena, Alday, called the flux tube approach. And that approach gives us information in a particular limit that is valid for any function of this finite coupling. So it's non-perturbative or finite coupling results. And it sort of expanded in another quantity, the number of excitations propagating along the flux tube, which translates into a kinematical variable here. So you actually have different stripes coming down here, or orders, like you have loop orders over here. And so one can test these 2 approaches, a bootstrap approach for perturbative gluons and arbitrary kinematical variables, and a flux tube approach here. And there's a massive amount of overlap and agreement of the results. But of course, the holy grail, this castle in the sky, would be to have results that are valid for arbitrary coupling and arbitrary kinematical variables. So we're not there yet, but we're trying to build up step by step from perturbation theory in the bootstrap approach. Now, the arenas where this has been the most successful so far have been 6 gluon amplitudes through 7 loops and 7 gluon amplitudes through 4 loops. But there's an even simpler arena, and I want to introduce bootstrapping to you using that arena because it's even simpler than 6 gluon amplitudes. And we only started to explore it in the past year or so. Now, one little drawback of the 6 of the pure gluon amplitudes is that because of dual conformal symmetry, the number of kinematic variables that the main part of the function depends on is different in QCD compared to that in planar n equals 4. There are 5 more variables in QCD than in planar n equals 4. So what we're going to see in a second is that there's another arena where the number of degrees of freedom or kinematic variables in QCD and planar n equals 4 are actually the same. And the number is going to be 2, which is even smaller than the 3 for 6 gluon amplitudes. And furthermore, it's likely that there's an even closer relation between QCD and planar n equals 4. So this motivates turning to a different problem. So this is a problem that I worked on with Andrew McLeod and Matthias Wilhelm in December. And I'll also show you some new results that push it further in collaboration with Andrew and Matthias and also Omer Gerdegan. So this process you could call Higgs amplitudes, but it's really an n equals 4 Super-Yang-Mills analog of that. But you can motivate it by thinking about Higgs production at the Large Hadron Collider. The dominant method for producing the Higgs at the LHC is when 2 gluons fuse together. They don't produce the Higgs directly because the Higgs is uncolored, but they couple to the heaviest particle in the standard model, the top quark, and it has a large Yukawa coupling to the Higgs. Now this top quark is totally virtual in most of the time, and so you have a loop diagram that characterizes this vertex at leading order in the QCD. But furthermore, the top quark is very heavy, and if you're producing the Higgs in this direction, the sort of relevant energies going through there should be compared with twice the mass of the top. Whereas, and that amounts to about 350 GeV. This is quite a bit larger because these things usually appear squared. It's quite a bit larger than the Higgs mass, which is only 125 GeV. So it's actually an excellent approximation to integrate out the top quark and replace its effects by what happens when you sort of shrink this vertex to 0 size. When you shrink it and integrate it out, you get many different operators, but the most important operator, the lowest gauge invariant operator that couples the gluons to the Higgs, is to just multiply the Higgs by the QCD Lagrangian, which involves the gluon field strengths G mu nu summed over color. And that operator is then a quantity that you can calculate its matrix elements with on-shell gluons. And that's of great importance to describing Higgs production at higher orders. For example, you could have 2 gluons coming in, producing the Higgs, and 1 extra gluon. There are also form factors with more gluons, but we're going to focus on this particular one, a gluon with 3 gluons, a Higgs with 3 gluons. So the Higgs is a scalar and a color singlet. In QCD, its amplitudes with gluons are matrix elements of this gluon operator with on-shell gluons. So you insert the operator and take a transition matrix element to multiple gluon states. These can also be referred to as form factors. Now in n equals 4, the supersymmetry means that operators are organized into supermultiplets. And this element is part of the stress tensor supermultiplet. This is a BPS protected multiplet. That means that it doesn't have any anomalous dimension in n equals 4 Super-Yang-Mills. Other elements of this multiplet include operators with a scalar, complex scalar, and its complex conjugate. And they should be arranged in some sort of traceless fashion so that they don't correspond to the singlet of SU4, which would be like the Konishi operator, which does have an anomalous dimension. Anyway, these traceless ones sit in the stress tensor multiplet, so you can also compute with scalars instead of gluons. But here I'll just refer to the corresponding amplitudes with gluons. Now, we could look, of course, the Higgs doesn't produce a single gluon. That would violate color and momentum conservation and stuff. This generic mass momentum operator. But we could make two gluons. And in fact, the Higgs decay to two gluons is a legitimate process. And the original gluon fusion, the virtual corrections, involve this form factor. The problem is that it's just too simple to bootstrap. In order to bootstrap something, we have to have functional dependence that's non-trivial. And this quantity has only one invariant in it. And therefore, it's just a set of numbers apart from an overall dependence on dimension, which at L loops would be something like S12, the momenta of the two gluons, or the Higgs mass to the minus L epsilon. In contrast, the Higgs 3-gluon form factor is just right. It depends on a certain number of dimensionless ratios, but not too many, 2 in particular. So on the next slide, we're going to look at the phase space for the Higgs to 3-gluon form factor and how many dimensionless ratios this quantity can depend on. So we have 3 gluons with momenta K1, K2, and K3, which sum up to minus K Higgs in the all outgoing momentum conservation conventions. So if we take the sum of all 3 of these and square it, we'll call that momentum invariant S123. But if we also expand out the dot products and recognize that Sij is Ki plus Kj squared for the 2 particle invariants, we find that S123 is just the sum of S12 plus S23 plus S31. So this is the familiar, say, Mandelstam relation for the S plus T plus U equals the sum of the external masses, which are all contained in the Higgs mass. So this relation, let's divide it by M Higgs squared, or by S123. And let's define the ratios that appear when we divide that through by U, V, and W. Notice that these are ratios, but they're not really cross ratios. And so the 3 of them, U, V, and W, add up to 1. So we can eliminate W and just consider the kinematic plane to consist of U and V, where W is 1 minus U minus V. On the other hand, sometimes it's useful to keep track of W because there's a dihedral symmetry in this picture. So the dihedral symmetry permutes 1 to 2, 2 to 3, and 3 to 1. So that's the cyclic symmetry. That takes U to V to W and back to U again. So that's a order 3 transformation, one of the generators of S3 or D3, the dihedral group. They're equivalent. And you can also do a flip, which is the other transformation. And you can flip along any of 3 axes. For example, you can exchange U and V. That would correspond to exchanging momenta K1 and K2. And it turns out that this n equals 4 amplitude, these stress tensor form factors are invariant under this whole dihedral group, D3 or S3. So you should imagine that you have the freedom to rotate around this triangle. So this triangle here denotes the boundaries of the phase space. So in region 1, the U, V, and W are all positive. In that region, if we take S123 M Higgs squared to be greater than 0, then these other invariants, S12, S23, and S31 are all positive. That corresponds to positive invariants correspond to gluon momenta, both in the same direction, both outgoing. So this would be for Higgs goes to 3 gluons. Now it's actually, you would get the same thing if all the momenta, all the invariants were negative too. These would still be positive. So we call this a Euclidean or sometimes a pseudo-Euclidean regime, because it's as if all the momenta were invariants were Euclidean or space-like. Now, as you take one of these invariants to 0, you can cross into other regions. So this is where S12 goes to 0 would be over here, where U goes to 0, or V goes to 0, or W goes to 0. And the first one you cross into when you do that is a scattering region. But when you do that crossing, you find that S123 is actually negative. So you have S123 negative, and then the numerators, one is positive and the other two are negative. So this is a scattering region, like glue goes to Higgs glue, except, or Higgs glue goes to glue, in the sense that the Higgs has to carry a space-like momentum. So it's not really a physical Higgs particle. So that's the region 2A. And by symmetry, cyclic symmetry, as you rotate this diagram around, this triangle around, 2A moves to 2B, moves to 2C. So those are scattering with space-like operators. And then finally, there's 3A, 3B, 3C. And this is the case where the Higgs has time-like momentum. So it's really like glue goes to Higgs glue. Of course, we're doing this all in the n=4 case, but the kinematics are exactly the same as if this operator were really a Higgs boson of various masses. So when you work out the one loop integrals, well, we actually saw one of these already before. Here, if this is the Higgs, then that's a massive leg, and you get these this function I showed before, which in terms of cross ratios, this becomes 1 over U, 1 over V, and logs of U over V. Now, at 2 loops, there was a computation by German, Jacquier, Glover, and Kukutsakas back in about 10 years ago, where they computed the answer for this process in full QCD at 2 loops. Soon after that, Brandhuber, Travaglini, and Young computed this n=4 version of it, the stress tensor 3-point form factor. They found something pretty amazing. They saw that the maximally transcendental part of the QCD result, which had weight 4, for both independent helicity amplitudes, you could have the gluons have plus, 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 or minus, plus, plus. There are 2 others that are related by parity, but these 2 are non-trivial in QCD, but they become the same at the maximally transcendental level. And those 2 functions at maximally transcendental level became the same. And furthermore, is exactly the same as the n=4 result. Now, there had been evidence prior to that of something called the principle of maximal transcendentality, the same kind of principle, but it was only applied to specific anomalous dimensions previously. These are the DGLAP or Altorelli-Parisi kernels and the BFKL kernels. This was seen, but it doesn't actually apply in the same way for generic scattering amplitudes. Even gluon-gluon scattering at 1 loop, there are pieces of the maximally transcendental part of QCD that don't really correspond to the n=4 1 loop amplitude. But in this case, it seemed to hold. And that's still an interesting open question. But that was sort of the situation 10 years ago. And the space of functions that were relevant for this problem were basically identified by German and Remedi. And they were defined as 2-dimensional harmonic polylogs. Now, they define it in a little bit different way, but as specific integrals. But we can also define them differentially by saying that every function in the space of 2D HPLs obeys the following properties. If we take the derivative with respect to U, we get things that depend on lower weight integrals of the same type with one fewer integration. And the main property is that the U derivative only produces these kinds of rational prefactors, 1 over U, 1 over 1 minus UV, 1 minus U, and U plus V. This is, of course, 1 minus W using this relation, and this is just W. And the V derivative is the same, except for the exchange of U and V. So basically there are 6 different quantities or lower weight transcendental functions that appear in this derivative. So the name of the game for trying to bootstrap this amplitude to go beyond 2 loops is to try to identify as small a subspace of this 2D HPL set of functions as possible and construct it to high weight. So that's going to conclude lecture 1, and we can take a break now before going on to lecture 2. Well, welcome back for lecture 2. So I'll remind you that at the end of the first lecture, we introduced this space of 2-dimensional harmonic polylogs, which were found to govern the structure of 2-loop amplitudes in for the Higgs to 3 gluon or glue to Higgs glue process by German and Ramidi, and also as a special example of that, the n=4 Super-Yang-Mills form factor as worked out by Brandhuber, Tralini, and Yang, also around the same time. Now, this space of functions was defined differentially in terms of these 6 functions at lower weight. And what we want to do is to find a space that is not this full space, because it grows rather rapidly, turns out, but a restricted subspace of it, and construct it to high weight. But before we do that, we want to introduce a little bit of general notation so that the same framework can be recycled from this form factor example into 6 and 7 gluon amplitudes later. And these cases all seem to live in a very special set of functions called generalized polylogarithms. And there was a lot of early work on this mathematically by Chen, which were called iterated integrals, somewhat more general. Also been explored by Goncharov and Brown. And there are these G functions defined by Goncharov, which are the entire class of functions that we'll need are contained in these types of functions. And they're defined iteratively. And I see I already have a typo. This x should be a t. And so you take the function with one less index, these ai's here. So this has n-1 of them in argument t. And then you integrate it d log of t minus a1, or dt over t minus a1 from 0 to x. And apart from some special cases when these indices are all 0, where you just use the log to the n of x, this is the definition. You can also define these quantities differentially. And if you differentiate with respect to x, you'll just recover a argument 1 over x minus a1, or d log of x minus a1. Now, when you have x dependence in the indices too, the differential isn't quite as simple, but there's a way of working it out. And so there's an alternative definition where you define the derivative, as we were doing in the 2D HPL case. You can define the total derivative as a sum over some set of d logs, where these SKs belong to a set which is called the symbol alphabet. And so there's a F super SK for each coefficient of the d logs. Now, this differential structure, or these set of iterated integrals, have a mathematical structure or a Hopf algebra that coacts on them. So action refers generally to multiplying together functions, and coaction refers to taking a function and splitting it into pieces. Now this function means the function space, in this case, this f. So a generic function will decompose into pieces that live in the same function space. So this derivative is one way of decomposing a function into into other functions that live in the same space. And often we will write the image of the coaction on a function as two pieces separated by a tensor product. Now, this logarithm has weight 1, and these functions here, because they're obtained by differentiating or removing one integration, they have weight n-1. And we can refer to this component of the coaction as having subscript n-1 comma 1 to denote these two weights, n-1 here and 1 here. So we will just refer to these functions that come out of taking the derivative, these coefficients, as the n-1 comma 1 coproduct of f's. So they're transcendental functions like f, just with one lower weight. And the number of them is naively equal to the number of elements of this symbol alphabet, the number of choices there. Oftentimes, there will be a lot of redundancies among these coproducts, so we'll take that into account later. Now, we can iterate this n-1 comma 1 coaction. So we take the derivatives of the functions fsk that appear here, and we or fsj, and we take the derivative and analyze them in the same way. And typically they will belong to the same, have the same d-logs. So there will be a single symbol alphabet that characterizes the whole space. And we can reuse this same formula. It's just that now we apply it to the quantities fsj, and we always denote their coproducts by putting the sk's that are summed over here in front of the sj. And we keep doing this until we can define mth coproducts if we do this m times. And then for a weight n function, the last time we can do this is n times. And at that point, we arrive at the symbol. So the symbol of the function f involves multiple sums over the letters of the symbol alphabet and a whole sequence of d-logs, n in number. And then the coefficient in front is just a set of rational numbers. And so these elements here, which multiply, are numbers multiplying tensors. And often to save space for the symbol, we don't show this logarithm anymore. It's understood. And we put tensor signs in front to keep track of the ordering in which things happened. So we have letters in an alphabet that we can choose from. There are 6 of them in this form factor case, 6 letters. And in principle, the symbol can have any 6 of the letters in any slot. Now that turns out to be a vast overcount. There are many restrictions we'll talk about governing how you can glue the letters together to make words, and then sum over the words to make legitimate symbols of legitimate functions. So these guys are now just rational numbers. So this the symbol was mentioned in this paper by Goncharov, Spradlin, Vergu, and Volovich, and has proved very powerful for analyzing the structure of transcendental functions, both in n=4, Super-Yang-Mills, QCD, and so on. So the symbol alphabet for HGGG, we can now read off from this definition. If you look at and compare this, these formulas with this sort of general formula, we see that the d-logs that appear are the differentials of logarithms of exactly 6 variables. U and V are manifest here. W is 1 minus U minus V appearing here. And we also see 1 minus U, 1 minus V, and 1 minus W. So the symbol alphabet is this 6-letter alphabet. And there are dihedral transformations that act on it that take U to V to W, and at the same time, these guys. And you can also flip or exchange U and V or any pair that you want. Now, an exercise for you is to use the differential structure, take derivatives of this box integral here and verify that all three permutations of this box integral are functions in this space. So now we need to try to ask, can we construct spaces just from these differential definitions? So suppose that we know all of the functions f at weight n minus 1. And let's suppose that the number of spaces in this at n minus 1 is dn minus 1. Then we can use this differential definition to construct all the functions the next weight up, and at least get an overcount of the number of functions. In the case of the 2D HPLs, because we have 6 letters, we might try to satisfy these equations with arbitrary functions for these 6 entries, fu, fv, fw, 1 minus u, 1 minus v, 1 minus w. Since we have dn minus 1 of them, if we multiply by 6, that's our naive guess for the number of functions that the next weight up. However, there is a constraint from integrability whenever you have functions of more than one variable. And that constraint is that all the mixed partial derivatives have to be equal. So if you take the derivative of f with respect to v and then the derivative with respect to u, that has to be the same as taking the derivative in the opposite direction. But it's not at all obvious that it should be true if we put in arbitrary functions in these two cases. So there's going to be a constraint that limits the number of parameters to be quite a bit smaller than this 6 times the previous. And your main homework exercise for these lectures is to work through the constraints that come from function level integrability. This shouldn't be confused with integrability of in the quantum field theory sense, but just the fact that we have a legitimate function. So you should use the equality of the mixed partial derivatives to derive a set of linear constraints. And these constraints will be on the double coproducts that have 2 indices on them. Because when you differentiate this definition here one more time, you will get derivatives of these guys, and that will involve the double coproducts. So, so you need to take those mixed partial derivatives and separate them out and see how many different constraints they apply. And that involves diagnosing the different independent rational functions of u and v that appear. And I'll just tell you what the answer is that you should find, which is these set of 9 equations. So one of them is the antisymmetric combination of 1 minus u, 1 minus v, and dihedral images. And there are 3 dihedral images of this equation. And then there's another equation that looks like this, and there are 6 dihedral images of this equation. You might not get the equations out in this form, but you should show that they're linearly equivalent to these equations. Okay, so now I've mentioned that there are a set of linear equations on the double coproducts that are involved in constructing these spaces. But now there's an important issue we need to talk about, which is quite a bit different, which is the overall normalizations of amplitudes. First of all, the amplitudes that we're talking about, which have massless external particles and massless gluons that can be exchanged between them, they're all divergent in 4 dimensions. And so they need to be regularized, but we also need to have some understanding of what these divergences look like. So a lot of this understanding was based on work in the 1980s and maybe early 90s in the factorization of QCD amplitudes. And it was done by people like Collins, Soper, Sturman, Mueller, Sen, Magnier, Korchemsky, and others. And what they realized was that if you have massless hard particles that couple to a gauge boson, a massless set of gauge bosons, non-abelian, then there's generically going to be a structure like this. So the amplitude is going to factorize into a hard part, which is infrared finite. And then there are going to be jets, which correspond to virtual collinear emission, that is virtual momenta that are approximately parallel to each hard outgoing line. And on top of that, there's going to be a soft function, which corresponds to gluons that couple to all of these hard lines, and then they can interact through the non-abelian vertices with each other. This factorization happens because the virtual collinear emission making up the jet, because it's all collinear or traveling in the same direction, to a soft gluon, it sort of looks like a single colored line. And because the soft gluon can't resolve things that are moving very close to each other, roughly speaking. And for the same reason, the soft gluon can't see this hard amplitude, which sits at very short distances. But the soft gluons are still quite a mess. The soft factor here is quite a mess kinematically in a general gauge theory, because there's nothing to keep the gluons from seeing all n of these hard particles. And so the more particles you have, the more invariance you have, and the more complicated this function can be. Fortunately, in the planar theory that is of interest to us now, there's a big simplification. And that's because the hard particles that appear, we're going to take them to be in the adjoint representation. And they have color quantum numbers that correspond to having two color edges according to a 't Hooft. So like this color will generically be different from this color. And furthermore, the color ordering or the planarity of the diagrams means that there's a class of contributions that just couple within each wedge, which is bounded by the color lines of each of the hard particles. So if we have a given soft gluon, it never crosses over from one wedge to another. That would be a non-planar Feynman diagram. So soft gluons can only be emitted and absorbed within a single wedge. And so at least as far as the non-hard part, the infrared divergent part of the amplitude is concerned, it can completely be divided up into these wedges. The collinear virtual emission can be assigned to wedges as well. So you get the square root of one jet factor in the previous picture assigned to this edge, this half of the wedge. The other one goes into the next one. But you also have a square root appearing over here. So this wedge itself is, at least at the level of divergences, is basically the square root of the 2-point amplitude, the Sudakov form factor. And that was studied, for example, by Meunier and Sturman. And furthermore, since we have this duality between this endpoint amplitude and expectation values of Wilson loops for polygons with n sides, when we perform this dissection into wedges, this wedge picks up a two semi-infinite light-like lines that meet at a kink. And this kink or cusp is the singularities in such a Wilson loop are associated with the cusp anomalous dimension. So there's a nice picture here where we have a divergence which has a very simple kinematic dependence because it can only depend on SI plus 1. And a similar functional dependence will appear at any loop order multiplied by various powers of logarithms of SI plus 1. And so what that means is that we can write down an expression that captures all the divergences of all the planar amplitudes. And we proposed back in 2005 the following formula to capture all of those, and also various finite parts as well. What we did was to define the BDS ansatz was to divide the the amplitude by the tree and write that quantity as the exponential of something involving the one loop amplitude. The one loop amplitude has these same cusp divergences, but it only involves the one loop cusp anomalous dimension. So to promote it to a solution to the divergences at L loops, we needed to multiply it by a function of epsilon, which at leading order in epsilon is the L loop cusp anomalous dimension. So they should have a little L on it here. And when you do that, and you also shift the this amplitude into you kind of multiply epsilon by L, you find that it solves all of the infrared divergences. It corresponds to all the infrared divergences of each of these webs. So this has a sum over terms for each of the SI I+1s, and each one of those terms reproduces the appropriate wedge. And then, since there could be finite remainders left over, we gave them constants. And that was motivated by the fact that when we did this for the 3-loop and 2-loop 4-point amplitudes, we found that the remainder was actually a constant. Now, this constancy is now well established for the case where there are 4 or 5 gluons, and it's really a consequence of dual conformal invariance. The dual conformal invariance is really well defined for things that are infrared finite and that can be defined completely in 4 dimensions. But the full amplitude has these infrared divergences. So you only discover things that are dual conformally invariant once you remove those divergences, either by factoring off some function like this or by taking some ratios or something like that. But then once you have established a finite remainder, then it actually has to be a constant for n equals 4 and 5 because there are no cross ratios on which it could depend. So this remainder function as an actual non-trivial function can only first happen at n equals 6. And that's when this BDS ansatz was found not to fail, to not describe the endpoint amplitude at the first time. It's rigged to describe the 1-loop amplitude, so 2 loops and 6 points was really the first place it could fail. But we can still define something left over by dividing the true answer, the Mhv amplitude, by the BDS ansatz, and defining in that way the exponential of a remainder function. And the dual conformal invariance implies that this remainder function only depends on a smaller number of cross ratios, the 3n minus 15, whereas these individual guys, they depend on individual Mandelstam invariants and not the cross ratios. Now, by putting the 1-loop amplitude up in here, that had nice collinear properties, and it implies that collinear properties of the BDS ansatz are correct, and therefore they shouldn't be messed up by this remainder function. And in particular, it implies that as any 2 gluons become collinear, the remainder function at n points should go into the remainder function at n minus 1 points. And in particular, the remainder function at 6 points should go into the remainder function at 5 points. But at 5 points, there were no non-trivial functions. We can define the constant part into a constant associated with the 5-point BDS ansatz, and therefore the remainder function at 5 points is 0. And so the remainder function has to vanish when any 2 gluons become collinear. So I've been sort of introducing this from the place where it first came in n gluon amplitudes, but there's a exactly identical story for the Higgs 3-gluon form factor. You can define a remainder using the corresponding 1-loop amplitude, and it has to have the same collinear property where the 2-gluon guy has no kinematic, no non-trivial kinematics, and so this 3-gluon remainder must vanish in all collinear limits as well. Now, it's nice to have a function that is 0 on the boundaries of the phase space. So the remainder function has some nice properties. However, it has issues. It has issues with its causal properties. In particular, it's going to have issues with overlapping branch cuts. And therefore, the remainder function will not live in the smallest space possible, and we'll have to define another kind of quantity, because we need to get our functions into as small a space as possible in order to be able to bootstrap them. If the function space is too big, you just have too many constants to fix, and it's too much work. So what's the problem with the remainder function? Well, one of the problems is that it's defined as through an exponential, and we really shouldn't do that. But let's talk about another problem, which is that we divided the true amplitude by the BDS ansatz. And the BDS ansatz includes the exponential of the full one loop amplitude. So here's the one loop amplitude here, and we've exponentiated it. If you expand this out in perturbation theory at 2 loops or second order, you'll find the square of the one loop amplitude. And that's going to cause problems. The square of the one loop amplitude is going to violate certain relations that are dictated by causality called the Steinman Relations. So the Steinman Relations go back to the 1960s, and they were largely forgotten by a lot of physicists, but Lopatov and collaborators Bartels and Sabio Vera resurrected or used them in the analysis of the 6-point amplitude in planar n equals 4, and basically argued that the BDS ansatz couldn't be right based on it, and they were absolutely correct. And so the Steinman relations are the statement that the amplitudes should not have branch cuts in overlapping channels. So an overlapping channel is one where you draw a cut that separates things into 2 pieces having that variable. When the 2 cuts are forced to cross, then you should not have overlapping branch cuts in those 2 channels. So here's a 6-point example where we have one cut here, and that cut is a representation. If you saturate it with intermediate states and integrate over a phase space, that will give you a discontinuity of the 6-point amplitude in the channel S123, because here's K1, K2, and K3 on one side of the cut. Whereas this cut here will have invariant S234. And the reason why this is not allowed is because you cannot draw any contribution to this discontinuity, which has intermediate particles running in one direction. Those are incompatible with the particles you need to be running in the other direction for the next discontinuity. So there's sort of no way to see how to draw a Feynman diagram representing such a double discontinuity. So this is a heuristic reasoning. Steinman applied very axiomatic quantum field theory arguments to come up with that conclusion, though. So that's a disallowed double cut. But some double cuts are allowed. For example, in the 7-point case, you could have a cut through S123 and then a cut through S567. And that double discontinuity would be allowed. And it would have a interpretation where you sort of divided this into 3 blobs, where you first, you can rescatter in this, across this line. You can saturate this with intermediate states. And then you can also do the same thing over here. And so those would be contributions to an iterated discontinuity. So you can't apply this kind of reasoning to 2-particle cuts in the massless case because they're not independent enough. When you take a 2-particle cut and you ask what happens when you move across the cut, you need to move one particle from incoming to outgoing. And that moves other variables around at the same time. And so it's very difficult to make sense out of this in the massless case. In the massive case, you can make sense out of 2-particle cuts. But in the massless case, we sort of can only start the analysis with 3 particle cuts. And that means that the first impact is at the 6-point amplitude. So the net summary is that we have a set of constraints on amplitudes that come from overlapping 3 particle cuts. And one example of them at the 6-point case is this one here, the discontinuity in the 1, 2, 3 channel, and then discontinuity in S3-4 must vanish. The problem with the BDS ansatz is that it has the square of the 1 loop amplitude. And here's what the 1 loop amplitude looks like, just from inspecting it from direct computation. It has a form where the poles are given in this function M6 hat. So these are poles in epsilon, double poles from overlap of soft and collinear singularities. And there's a 1/epsilon pole in here. And then there are also these finite parts that depend on the individual Mandelstam variables. And then there's a more complicated part, but it only depends on these cross ratios, U, V, and W, that we defined earlier, involving double ratios of Mandelstam variables that are dual conformally invariant. So this is the full 1 loop amplitude. And the problem is that these pieces here contain dependence on the 3 particle invariants, and they have cuts in all possible channels. Well, it's sort of symmetric. So if you have a cut in one 3 particle invariant, you have a cut in the other one. And furthermore, when you square this, then you will get double discontinuities from taking a cut in one 3 particle invariant and then a cut in the other one, in the other factor. So this guy violates the this double discontinuity relation. So if we have him in the denominator, then this remainder function is also going to violate it, because the thing on top didn't violate it and the one on the bottom violated it. But what we can do is we can replace the BDS ansatz with something that was referred to as the BDS-like ansatz in this paper. And that one discards from M6 the complicated problematic part, finite part here, called calligraphic E6. So we're going to remove that and define the BDS-like ansatz just involving M6 hat, throwing this guy out of it. Okay, so the nice thing about that is this has only 2 particle invariants in it, and therefore its double discontinuity in 3 particle invariants is 0. So when we divide by this quantity, we get something that's very nice with respect to the Steinman relations. So we call that curly E6. Now, if you go back through the difference between BDS and BDS-like, it totally involved this function here, E6(1). And so it gets multiplied from this function of epsilon as epsilon goes to 0 by the cusp anomalous dimension over 4. So we have this sort of fundamental relation between the remainder function with good collinear properties and the function E6 with good Steinman properties. And that will allow us, when we get to the 6 gluon case, to define a almost minimal function space that contains the 6 gluon amplitudes when we normalize them like this. And there's also a Steinman preserving normalization factor for 7 gluons. 8 turns out to be a little bit trickier. So, I mean, I was trying to introduce the form factor, and in the case of the form factor, there's only one 3 particle invariant, and you're always allowed to have discontinuities in the same channel multiple times. And therefore, there aren't actually any Steinman relations to preserve, but I wanted to motivate the fact that if you choose the right normalization, you may be able to simplify the results a lot. And the remainder function is typically not the right normalization. So we want to find something closer to this curly E6. So what do? Well, we do the same thing that was done in the 6 gluon amplitude, we go and look at the one loop form factor for Higgs to 3 gluons. So call that M3. And as in the 6 gluon case, it has a minimal part, which looks like this. And it also has a non-trivial quantity made out of the conformal cross ratios U, V, and W. So I've split it off here as this curly E1. Now, actually, there's a bit of an ambiguity because there's also this green guy here. This green guy is just made out of logarithms of the 3 UIs, where U1 is U, U2 is V, and U3 is W. And this is dihedrally invariant, so it has all the right symmetries, and it's also dual conformally invariant. So there's some ambiguity of where you should put this, whether you should put it in M hat or put it in here. And we tried both, but the answer is it's better to put it in M hat, M3 hat. This should be a 3, sorry. So when we do that normalization and use only this M3 hat in the corresponding ansatz for the form factor, we find that the quantity E, now with no 6 on it, just to represent the form factor, and we took the subscript off of R to represent the form factor remainder function, it has exactly the same relation between E and R as we had in the 6 gluon case. It's just that now we need to use this function here, which is actually extremely similar, except maybe for normalization, to the one in the 6 gluon case. Okay, so the bottom line is we have a proposed normalization for a function curly E. And now we can inspect the results not only at 1 loop, but also at 2 loops and compare them. Now let's just look a little bit closer at this relation between the remainder function and curly E. It involves the cusp anomalous dimension. Now, one of the things that means is this relation tells us we don't really need to look at R until the very end if we want to, because the collinear limit of R is going to vanish. And we can enforce that just by requiring the collinear limit of E to go to this quantity, which is easy to compute. So to satisfy the collinear vanishing of R, we just need to impose this relation. And then we can kind of throw away R and just bring it back later. Now, what is the cusp anomalous dimension? So this is a quantity that was computed using integrability techniques to all orders by Beissert, Eden, and Staudacher. And they gave a very elegant description of it in terms of a kernel of a semi-infinite matrix that was computed by integrating Bessel functions. But here we're just going to take it for given that we know it to all loop orders. And furthermore, its perturbative expansion only involves zeta values or constants. Since it's just a function of the coupling, it would have to be constants of some type. And the symbol, these carry a given weight because these are sort of iterated integrals with fixed upper endpoints. And the weight for an ordinary zeta value is just the subscript on it. So we see weight 2, weight 4, weight 6, weight 3 plus 3 is 6, and so on. And here, G squared is, this is the integrability definition of the coupling. Lambda is the number of colors times the Yang-Mills coupling squared. Now, at symbol level, these weight 8 functions are just constants. Since the symbol is obtained by differentiating n times, basically, and these are constants, the symbols of the zeta values all vanish. Therefore, at symbol level, we can replace gamma cusp over 4 just by G squared. And we can write the relation between E and R at symbol level in this form. And now we can expand out the exponential, and we get 1 at order G squared to the 0. And then at leading order, well, the remainder function vanishes at 1 loop. So we just get E1 back, as we should. And then at 2 loops, we get the 2 loop remainder function, but we also get from the second order term in the Taylor expansion of the exponential, 1/2 of E1 squared. So we see that E2 is just R2 plus 1/2 E1 squared. And of course, you can use this relation to relate E and R at any loop order in terms of lower loop quantities. But this is the symbol level example. So now we can go inspect the two loop symbol. And the starting point is to see the symbol that was computed by Brandhuber, Travaglini, and Young. And they got a formula something like this. So it's a wait for symbol. So every term in it should have 4 slots. And we'll notice a few features. It always starts with a U or a V or a W. Well, these are all U's, but you're supposed to add over cyclic permutations, and that will induce V's and W's in the first slot. Also, you'll notice that the last slot always has a form which is 1 minus U over U, or 1 minus V over V, or 1 minus W over W. Nothing else happens in the last slot. And on the other hand, even though it only has 84 terms when you sum over the cyclic permutations, every pair of adjacent letters seems to appear. U's are next to V's and W's, V's are next to 1 minus U's, and 1 minus U's are next to 1 minus W's, and so on. So, but we thought that from this analog with the Steinman relations, that things might get simpler if we don't study the remainder function, but study something closer to the actual amplitude. And normalizing by this BDS-like ansatz, we find that we should be looking at not R2, but we should add 1/2 of E1 squared. So when we add that, we find that some pretty amazing simplifications happen. To make the simplifications as amazing as possible, we're going to switch to a different alphabet. And this alphabet was motivated by something in the 6 gluon case. And so what we're going to do is we're just going to take some rational combinations of the original 6 letters, U, V, W, 1 minus U, 1 minus V, and 1 minus W, and define these quantities. You could motivate this by the fact that that's what appears in the last entry of the two-loop symbol. And then there are these ratios here, which as we'll see later, these combinations are nice in the 6 gluon case. So we try them again here. Well, when we do those 2 switches, we convert from R to E, and we switch to this alphabet. We find an amazing collapse of the 1 and 2 loop amplitudes. They're, apart from dihedral images, they have just 1 and 2 terms respectively. So the 1 loop amplitude has a -1, and then B in the first slot and D in the second slot. And then if you sum over dihedral images, you get 6 terms in all. The 2 loop amplitude, this is an even more amazing collapse, has only 12 terms, which can be grouped into 2 dihedral orbits as well. And one of them has B, D, 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 and the other has B, 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 D. So there's a vast simplification that takes place when we change the normalization and also use this alphabet. So as an exercise, if you like, you can take E1 and compute its symbol. Since it's originally given in U, V, and W, you could do it in that frame, or you could substitute in for U, V, and W by solving these relations for U. So U is 1 over the square root of BC. Anyway, then you can work out its symbol and verify that it's equal to this. And another useful thing when you have 2 symbol alphabets is to know how the coproducts are related to each other. So another useful exercise is to derive these relations plus their dihedral images that connect coproducts in the U, V, W alphabet with those in the ABC alphabet. So when you go further in this space, beyond 2 loops, you find that there are many constraints on what letter can appear next to what other letter. For example, D and E can never appear next to each other in the symbol, which can be codified by saying that the double coproducts of D of E first and then D vanishes, and also E first and then D. And these are the cyclic images of it. So there are 6 relations like this. So this was used to define a space we called M in this paper. And these constraints are actually obeyed by all of the integrals that Gehrman and Remedi computed 20 years ago for this process at 2 loops, both planar and non-planar. And so they are a property of QCD, at least through 2 loops. And on the other hand, there are some new relations which were only recognized a little more recently that also forbid the adjacency of A with D, B with E, and C with F. And these relationships hold for planar n equals 4 super-Yang-Mills amplitudes, and we now have evidence that they hold up through 8 loops. So that's quite a bit further. Here's just a little mnemonic. It's a kind of a prism compressed into a plane, which lets you remember how these letters are connected to each other. So under dihedral symmetries, you just enforce the symmetries of this diagram under cycling and under reflections. And the dashed lines are to remind you of all the things that are forbidden. So there are 6 dashed lines that are forbidden. And that corresponds to these 12 forbidden pairs in this space. So let's recap this, what the situation is for the relations between double coproducts. In this new alphabet S prime, well, remember there were 9 integrability relations. What you can also do if you want is to transform from the UVW letters in which you derived them for the homework. You could transform them into this new alphabet. When you do that, after taking some linear combinations, you find that 6 of the 9 integrability relations become anti-symmetric parts of the 12 relations. So they become things like FD minus FE equals 0. Whereas there's also a symmetric part, FD plus FE equals 0, and so on. So these 12 relations have 6 anti-symmetric parts, and that's 6 of the 9 integrability relations. But there's still 3 more integrability relations, and they turn out to have this form. 2 of them are not too long, it's pretty short. And this one is quite a bit longer. And this is this long one involves all 6 of them, A, B, C, D, E, and F, with this extra piece here. So at the end of the day, if you ask about how many allowed pairs there are of adjacent symbol letters, they're encoded by the fact that you naively have 36 of them, 6 times 6, but we've removed 9 anti-symmetric guys and 6 symmetric guys, or a total of 15. So there are 21 allowed pairs. And you might ask, how do we know there might be fewer than that? Well, we found by the time we got to 3 loops that all 21 pairs are independent, and there are no generic relations between the 21 pairs that would reduce it to lower numbers. You need all of them, with the evidence being taken out of the 3-loop symbol. Okay, so that was the situation for the pair relations. They're all given on this slide. Now, we also have branch cut conditions, and these branch cut conditions will constrain the symbol as well. So the branch cuts for massless particles always start where an invariant goes through 0. So this is an example of a rescattering which can take place where the Higgs scatters to 3 gluons, and then 2 of them rescatter. And the place where this cut opens up is when these guys get above threshold. But because these gluons are massless, all you need to do is make S12 greater than 0, and then you're above threshold and scattering happens. When this variable is negative or space-like, there is no scattering. So the branch cut opens up at S12 equal to 0, and similarly for S23 and S31. And then there's also a scattering in the Higgs invariant itself in S1, 2, 3. So the conclusion of the branch cut analysis in terms of the Mandelstam variables is that they should only start at 0. But the Mandelstam variables can also appear in the denominator of the U's, V's, and W's. And therefore, you can have branch cuts at 0 or infinity in these 3 variables. But that's the only place you can have them. In particular, a variable like 1 minus u, when it goes to 0, that says that S123 goes to S12. And that is just not a generically allowed branch cut. And so we need to forbid logarithms of 1 minus u from ever appearing in the weight 1 sector. So the only weight 1 functions that were allowed are not 6, but only 3 of them: log u, log v, and log w. Now, another important point is that when we take a derivative of a function, that commutes with the action of taking the discontinuity. So taking the derivative with respect to z of the discontinuity of some function at some value z0 can also be obtained by taking the derivative first and then taking the discontinuity. And this commutation is sort of reflected in the symbol. To integrate up the symbol and impose the branch cut conditions, it must be true that the derivative has to obey the branch cut condition. Or to say it a different way, when we build the space up from weight 1, we can have only the first entries of the symbol be these 3 letters, U, V, and W. Or we could transform according to this change of alphabet. And you see that that change of alphabet mixes U, V, and W with A, B, and C. But the first entry condition is that you can't have D, E, and F in the beginning, only A, B, and C. Now, this branch cut condition, actually putting the condition that only U, V, W or only A, B, C in the front, that's not sufficient. It's necessary, but it's not sufficient. And we actually need to require a further condition, which is obtained by taking the U derivative and looking in the vicinity of U equals 1, and especially the region where V and W go to 0. And when you do that, you find that this 1 minus U coproduct must vanish when U goes to 1 and V and W goes to 0. And this condition is actually stronger than the first entry condition. And it says at the symbol level, it says that if you find a 1 minus U anywhere in the symbol, then somewhere in front of it, there must be either a U or a 1 minus V or a 1 minus W. These quantities, when we go into this region, they all go to 1. And therefore, when a letter is 1 in the symbol, that's like the log of 1, that vanishes. That causes the symbol to vanish. And so therefore, this 1 minus U must be sort of protected by, by putting one of these 3 letters in front. Now, for 6 and 7 gluons, it's actually a little simpler. And at symbol level, it's enough to impose that the first entry condition is that entry that allows the branch cut condition to be maintained all the way through. So here's a heuristic picture of the function space, which more or less applies to both the space we need for the form factor and the space we need for 6 gluon amplitudes and so on with appropriate modifications. At weight 0, we have the function 1, the constant. At weight 1, we have the logarithms allowed by the first entry condition, log U, log V, log W, or UIs. At weight 2, we have these functions. We've seen them already in the one loop integrals, and we have various logarithms. And then at weight 3, we start to get classical polylogs, but we also have true 2-dimensional HPLs cropping up here. And scattered through here are various simpler functions, but also 2D HPLs. And everything is sort of built up based on this one relation and its image under U goes to V. So we can now try to construct this space in a little bit more detail. And at weight 2, it's quite simple. So we'll just do that exercise. So at weight 2, the first letter must be A, B, or C. Now, at first sight, we could put 6 possible choices of letters in the second slot, but we have a lot of constraints from these various pair relations. So first, suppose that the second letter is also drawn from A, B, or C. If that's the case, then we're going to go back and look at the longest pair constraint, which is right here. So if both letters were from A, B, or C, then we can set anything with a D, E, or F to 0. Well, that's almost everything here. So the only thing left is this guy. So we have to impose FCB equals FBC. So we do that. And then when you look at the other 2 longer pair constraints and combine it with that, you find the dihedral images. So these are more or less just saying that if you only have A's, B's, and C's, you can treat A, B, and C as independent variables and just write down symmetric tensors involving them. So this A tensor A, that is the symbol of 1/2 of log squared of A, as you'll see if you take this derivative with respect to A. And A tensor B plus B tensor A, which is allowed by this equation and the other ones, that's the symbol of log A, log B. And you take these guys and you include their cyclic images and you get 6 functions. Now we go back and we allow the second letter to be D, E, or F. Let's suppose it's D. If we let the last letter be D and we go back to that long pair constraint, then we find that it collapses to FBD equals FCD. So we can satisfy that by having the combination B tensor D plus C tensor D. That's an allowed combination. If we rewrite that combination back in the original alphabet, it turns out it only involves U. So we see that it's actually the symbol of this quantity, Li2 of 1 minus 1 over U. And then we get the cyclic images of that. So that's all that's allowed. And so we find that this weight 2 space has 9 functions in it. We could do the same exercise at weight 3. We start with all 9 weight 2 symbols, and we tack on 6 choices of letters in the third slot. So naively, that would be 54. Now, of course, there are lots of pair constraints that will knock that down to much lower than 54 pretty quickly. And then we also apply the branch cut constraints. Those I didn't apply at weight 2. If I had, you would have seen that they were automatically satisfied. Well, you can see that the only thing with a U in it had, with a 1 minus U in it, had a U in front of it, which sends it to 0 in the vicinity of U equals 1. So anyway, but they're non-trivial constraints at weight 3. And finally, there are some triple constraints, which were observed empirically. There are four such equations. So it's handy to solve it on the computer, at least at first. And you find that the weight 3 space is 21 dimensional. So this was describing the construction at symbol level, but the promotion to functions is typically not very difficult. And at low weights, most of these functions are logarithms and 1D HPLs. So the 1D HPLs were originally defined by Remedi and Vermaseren, and their integral definition looks like this. Every time you have they're defined for a weight vector W, which just has zeros and ones in it. And if the first entry is a 0, you define it by integrating dt over t. And if it's 1, you define it by integrating dt over 1 minus t. Except for some annoying sign differences, it's a special case of the g functions that we defined earlier. When you take the derivatives, you find that the derivative with a 0 in front gives you a d log x, and a derivative if it had a 1 in front clips off the 1 and gives you a d log of 1 minus x. This tells you that the symbol alphabet for this space of functions has just 2 letters, x and 1 minus x. And although in general we have more letters and we need 2D HPLs, at low weights, those functions don't enter too early. So in fact, we can write down the function space version of these symbols we constructed previously. If we let U be U1, V be U2, and W be U3, then the 3 weight 1 functions are just the log of the UIs. The 9 weight 2 functions are log squareds of UIs in various combinations, and also this harmonic polylog with 2 indices, 0, 1, with argument 1 minus UI. If you put a UI in the 1 minus UI as the argument and the 1 in the back, that typically makes the function well behaved at U equals 1. In terms of the weight 2 functions, 5 of the orbits are pretty simple. That is, they don't involve true 2D HPLs, and they're written down here. And then there are 2 more complicated 3 orbits. And then there's a zeta 3 potential constant. When we wrote the paper back in December, we didn't think zeta 3 was there because it didn't seem to be needed through 5 loops. But it does start to pop up at 6 loops. So live and learn. Now, you can represent all of these answers in terms of the symbols, but I want to try to convince you that the symbol representation is too verbose. And what I mean by that is that the number of terms in the symbol grows by about a factor of 20 each loop order. This 2-loop symbol having only 12 terms, that was pretty anomalously small. By the time you get to 3 loops, you have 636. And by the time you get to 7 loops, I counted it yesterday, and you have 97,594,968 non-vanishing terms. So you don't really want to print that or even save it in an ancillary file anywhere. So instead of having this verbose, maximally iterated symbol representation, we're just going to use this differential representation iteratively. So we're going to define everything like a collection of Matryoshka dolls. You have the amplitude that you want, you define it by its first derivatives. What are the first derivatives? You define them by their first derivatives, and so on down the line. And in order to do that at a function level, we also need to specify the constants of integration for these first derivatives at one point. And for the form factor problem, we could choose this point to be where U goes to 1 and V and W go to 0. So more generally, for any polylogarithmic function space that's defined by this differential relation, you can completely characterize it in terms of what happens to the basis functions in that space. So if Fi at weight n are a basis, so I runs from 1 to dn, the dimension of the space at weight n, so these functions are a basis for that, then you can take their derivatives and they'll be of this type too. And furthermore, you can expand those derivatives over the function space at one lower weight, which has basis fj n minus 1. So when you do that, you get this representation of the derivative, or equally of the n minus 1 comma 1 coproduct. And it's in terms of a 3-index tensor. So this tensor is a set of rational numbers, and it's the dimension of the tensor is dn for the index I, dn minus 1 for the index j, and the number of elements of the symbol alphabet as index alpha. So these tensors fully characterize the space at symbol level and up to the constants at function level, where the constants have to be fixed by selecting a base point. So that's the end of this lecture. In the next lecture, we'll talk a little bit more about doing the bootstrap, taking into account the certain sets of final entry relations that we can discover at each order in the loop expansion. And then we'll show some results. And then in lecture 4, we'll apply all this technology to multi-gluon amplitudes as well beyond the form factors. Thanks.